Welcome to the Deep Dive. Today we're jumping into the single biggest event in machine learning research, NeurIPS 2025. And we're going to try and synthesize what actually matters from this, well, just this massive global output.
It was an event of just staggering scale this year. I mean, it spanned two cities, San Diego and Mexico City, which really shows you the field's enormous footprint.
And the numbers are just wild.
Oh, they are. We saw 21,575 valid submissions, and in the end, only 5,290 papers were accepted. That's a 24.52% acceptance rate. It's incredibly competitive.
That volume alone tells you the field is just accelerating. But what I found so fascinating about the 7 best papers and runners-up is that they signal a profound strategic pivot.
A pivot away from what, exactly?
Away from the brute force arms race, just counting trillions of parameters. And instead, it's a move toward architectural efficiency, theoretical rigor, and honestly, a necessary reckoning with the societal consequences.
Exactly. And before we dive into all the new breakthroughs, I think it's right to recognize the foundations. The Test of Time Award went to the piece of work that truly reshaped the landscape 10 years ago.
Faster RCNN, towards real-time object detection with region proposal networks from 2015.
That's the one. It just had such an enduring impact.
It really did. That paper basically created the modern paradigm for object recognition. And acknowledging that, we also have to pause and recognize the loss of its co-author, Dr. Jian Sun.
A true pioneer in computer vision. His work reshaped research paradigms, and his influence is still felt everywhere.
Absolutely. And recognizing work like faster RCNN, it sets the standard, right? Impact that lasts a decade.
And now the field is chasing that same kind of enduring impact, but by focusing on innovation beyond just raw size.
Okay, so let's unpack that shift, this move away from just parameter counting toward, well, architectural genius. And a good place to start is a segment of AI that has, for a long time, been surprisingly shallow.
Reinforcement learning, or RL. The RL community delivered a breakthrough that I think shocked a lot of researchers. It was a paper called 1,000-Layer Networks for Self-Supervised RL.
1,000 layers. I mean, you have to remember the context here. For years, functional RL models, especially for agents, they were, what, 2 to 5 layers deep?
At most. 2 to 5 was the standard. So going from 5 to 1,024 layers.
That's not an incremental step.
Yeah.
That is a paradigm shift. So what does scaling depth actually get you in RL that just making things wider didn't?
It unlocks a vastly increased capacity for hierarchical representation and planning.
Okay.
So when you're dealing with these unsupervised goal-conditioned tasks, like, say, complex robotic movement or manipulation, these super deep networks let the agent learn sophisticated goal-reaching capabilities that were just impossible before.
So depth is now a non-negotiable axis for building smart agents.
It reframes the whole field. It says, yes, there is enough signal in the environment to effectively train thousands of layers.
Which has huge implications for robotics. Now, speaking of architectural elegance, the large language model's base saw a surprisingly simple modification win a major award.
Gated attention for large language models. This is a textbook example of how a tiny intervention can solve these huge scaling problems.
So what's the modification?
It's actually really simple. You apply a head-specific sigmoid gate right after the scale dot product attention, or SDPA, output.
Okay, so for everyone listening, SDPA is the core engine, right? It's the mechanism that decides how much importance to put on different words in a sentence.
That's right.
So you're basically adding a little on-off switch, the gate, to the engine's exhaust pipe.
Precisely. And that simple gate gives you two huge benefits. First, it puts some crucial nonlinearity back into the attention mechanism.
And the second?
And this is the most important part for stability. It uses query-dependent sparse gating scores to regulate the output.
Why is regulating the output so important, especially in these massive models?
Because it directly fights against these persistent scaling issues. The biggest one is the attention sink phenomenon.
Let's pause on that. What exactly is an attention sink?
Okay, think of it like this. In a conversation, the first few words someone says are so interesting that everyone tunes out everything that comes after.
Right.
In LLMs, the first few tokens, the first few words, can just hoard all the attention no matter what comes later. This gate helps control that, which improves training stability and lets developers use much larger learning rates.
So for the user, the takeaway is just pure efficiency and robustness.
Yeah.
And we know this isn't just theory. It's already in models like the Qwen3 Next series.
It's a fundamental improvement that went straight to production.
And this all ties back to the theory of scaling, doesn't it? Like why these models actually get smarter as they get bigger.
It does, and another runner-up finally gave us the definitive mathematical answer. They found that representation superposition is the central driver behind neural scaling laws.
Superposition. That sounds like it's from physics.
Hmm.
How does it apply here?
It's the idea of fitting, say, 10 pounds of features into a 5-pound bag of model dimensions.
Yep.
LLMs represent more concepts than the actual number of dimensions they have. This ability to compress and overlay concepts is superposition. And the paper found that the stronger this ability is, the faster the model's loss decreases.
So it's the mathematical reason why spending more compute to make models wider and deeper actually works.
It is. It's the underpinning.
Okay, so section 1 proved we can scale architectures more efficiently, but this triumph immediately leads to this necessary self-critique, the intellectual limits and societal risks that come with that scale.
That's the critical checkpoint. The very tools we build for performance are creating new kinds of risk. And leading this whole section was the best paper on the artificial Hivemind effect.
The idea that if we all interact with these LLMs too much, it could lead to a homogenization of human thought. That sounds pretty serious. What was the evidence?
They used a massive data set called Infinity Chat. It had 26,000 real-world open-ended questions and over 31,000 human annotations.
And what did they find?
They confirmed a striking homogeneity. They saw repetition within a single model's answers, but more importantly, a shocking similarity across different models, even from different companies.
And intellectual convergence. But why? If they're all trained on different data, why are they all converging on the same ideas?
The paper points the finger squarely at our current alignment techniques. It found that the reward models we use, the automated judges, they're just miscalibrated to what diverse individual humans actually prefer.
So by optimizing for a generalized sort of averaged preference.
You actively suppress intellectual and creative heterogeneity. Alignment, as we currently do it, is actively driving the hive mind.
That's a huge challenge. If we optimize for safe or preferred,
Yeah.
we might just be optimizing for uniformity.
Exactly. And speaking of the limits of optimization, a critical runner-up paper questioned whether reinforcement learning even makes LLMs smarter in the first place.
Right. This was the paper asking, does reinforcement learning really incentivize reasoning capacity in LLMs beyond the base model?
That's the one. They focused on a common technique, RLVR, or reinforcement learning with verifiable rewards. And their key finding was a really important negative result.
What was it?
RLVR training definitely enhances sampling efficiency. It helps the model find the correct answer, the one it already knows, much faster.
But it doesn't fundamentally change its underlying intelligence.
Precisely. It does not elicit fundamentally new reasoning. It just optimizes within the base model's existing solution space. Sometimes it even narrows the model's reasoning capability.
So we're teaching it to be better at finding what it already knows, not discovering new things.
A vital distinction.
Wow. Okay, moving from reasoning to generation, we also got a huge theoretical insight into diffusion models, the tech behind image and video generators.
Right, about why they generalize so well without just memorizing their training data. The paper identified something called implicit dynamical regularization.
That sounds highly technical. Break that down for us. What does it mean for the user?
It means the training process itself acts as a regulator. The researchers found two predictable phases during training. There's an early generalization phase where it learns concepts, and a later memorization phase where it starts to overfit.
Okay.
And critically, the start of that memorization phase scales linearly with the dataset size.
So if you double your training data, you effectively double the amount of safe training time before the model just starts spitting back copyrighted images.
That's the idea. It fundamentally postpones overfitting, which is why we can train these things on just massive datasets and get such creative results.
And finally, on the theory side, a paper resolved a 30-year-old open problem in online learning.
A really deep, fundamental question about the benefit of seeing unlabeled data before you have to make a prediction. They established the optimal mistake bound for what's called transductive learning.
And what's the big takeaway there?
It proves there's a quadratic gap in performance. It means having that advanced look at the data offers immense theoretical value. It's a huge validation for the power of context.
Okay, so if the technical papers were the thesis, then the invited talks from the big thinkers were definitely the antithesis. This was the moment for a fundamental reorientation.
Absolutely. The tension between engineering success and scientific understanding just came to a head. It started with Turing Award winner Richard Sutton, who basically said AI has become a huge industry and has lost its way.
So what's his path forward?
A return to first principles. He wants research focused on agents that learn continually, that require world models and planning, and that acquire high-level, learnable knowledge.
Which connects right back to that 1,000-layer RL work.
Exactly. Then you had Zeynep Tufekci, who shifted the whole threat discussion. Everyone's worried about AGI. She said the real immediate crisis is AGEI.
Artificial good enough intelligence.
Right. She argues we don't need superhuman AGI to cause a catastrophe. The danger is that AGEI makes what's already possible cheap, easy, fast, and large scale. It's good enough to be destructive now.
And what does that destruction look like?
It's the immediate crisis of trust. AGI can blur or pulverize our existing mechanisms of proof of accuracy, effort, veracity, authenticity.
Deepfakes, misinformation, automated papers.
All at scale. It's an infrastructural risk. Our societal foundations of trust just start to collapse when they're good enough.
That feels so much more tangible than these far-off AGI scenarios. Then Yijin Choi addressed the limits of scaling, calling it jagged intelligence.
I loved that term, jagged intelligence. It's that frustrating, inconsistent performance we all see. The model aces a PhD exam but then fails a simple logic puzzle.
It's completely unreliable.
And Choi argues that this shows the fundamental limits of our current scaling approach. Our engineering has outpaced our scientific understanding.
And rounding out the critiques, Andrew Sachs gave some mathematical insight into why the models work this way, with his concept of the neural race.
Right, the neural race. It's a principle that describes how deep networks learn. As they train, different pathways compete to explain the data, and this biases the network towards shared representations.
So understanding that bias is the key to building models that can actually generalize reliably.
That's the hope. It's an attempt to explain why they converge on the internal concepts they do.
So we have these technical triumphs that are being tempered by this profound self-critique. Let's look at the community itself, starting with that incredibly intense review process.
Unprecedented. With over 21,000 submissions, the pressure was immense. We were hearing reports of papers with near-perfect scores like 5554 getting rejected.
Why reject a paper with reviews that good?
It seems the chairs were emphasizing novelty. They're moving away from just rewarding incremental quantitative gains. The bar for a truly new paradigm-shifting idea is just getting dramatically higher.
And looking at where the research is going, the focus is completely shifted to agentic systems.
Oh, absolutely. The dedicated workshop on multi-turn interactions in LLMs confirms it. They're tackling these huge operational problems, like how to handle sparse rewards, maintain alignment over long conversations, and evaluate strategic consistency.
Which is where frameworks like RIMA come in.
Right. Reinforced Metathinking Agents, or RIMA. It's a clever use of multi-agent RL where they decouple the problem. You have a high-level agent for strategy and a low-level one for execution.
And that improves generalization on really complex tasks.
It does. It's a blueprint for building more reliable agents.
The conference also heavily emphasized responsibility and global equity, especially at the Mexico City venue.
The ethical side was front and center. There was a critical tutorial on the science of trustworthy generative models, arguing that trust can't just be a patch you apply at the end. It has to be engineered in from the start.
And the global perspective was crucial, given where most of this training data comes from.
Precisely. The CDMX track had a pivotal workshop on centering low-resource languages and cultures. The goal is to fight the linguistic inequality and cultural erasure that happens when you only train on, high-resource Western languages.
The NeurIPS Foundation also launched the Bridging the Future Grants program.
Up to $50,000 to broaden participation in AI. It's a real push for diversity.
And then, in a very real-world nod, there was a social event I saw.
Oh, the negotiation workshop.
Claiming your true market value as an AI researcher.
It perfectly captures the moment, doesn't it? The intellectual bar is rising, the societal stakes are escalating, and the financial landscape is changing so fast that researchers need a workshop just to navigate their own careers.
This deep dive really shows a field in a profound, necessary transition. NeurIPS 2025 gave us these breakthroughs, like 224-layer RL, proving efficiency is the new scaling frontier. But those triumphs were mirrored by this foundational critique. AGEI, jagged intelligence, the artificial hive mind.
And whole focus is shifting.
It's shifting from how large can we make it to how efficient, trustworthy, and maybe most importantly, how intellectually diverse can we make it.
That shift from raw performance to intellectual quality is the central tension. We learned our alignment methods optimize what a model already knows, and that optimizing for general preference actively suppresses novelty. And now the frontier is building these thousand-layer agents that can potentially learn new things.
Which leaves us with this provocative thought for you. We are building systems that are deeper than ever before, systems meant to discover new paths. But if we can't measure or incentivize genuinely new diverse reasoning, if our own optimization methods punish novelty, how will we truly know when these massively deep agents discover something genuinely new? And how can we ensure that their innovation isn't simply a more complex, better optimized version of the hive mind?